Hey there, how's it going? So we've done sums, difference, products. So last basic operation is division, so quotients. So here let's start with an example. Have a squeeze out. Let's say we've got y equals x plus 2 all over x. Question, can we do this using our existing knowledge? Well, we can split this up because if we've got a sum or difference in the numerator, this is the same as x over x plus 2 over x. X over x is 1, derivative of that is 0, and plus 2 over x is 2 times x to the negative 1, constant times something with power, use the power rule, okay? So I'm not even going to do that, but what I'm going to do is move this plus 2 down here. Can we do this? No, because we can't split up some multiple terms in the denominator in the same way. Now, what I just said about when we had x in the denominator is we could change that to x to the negative 1. So likewise, we could change this bit here into, well, this is the same as x times 1 on x plus 2, and then 1 on x plus 2 is x plus 2 to the negative 1. So now we've transformed our quotient, taking one function divided by another, into a product. And then could we use the product rule? Yes, we could. So the quotient rule isn't strictly necessary because it's really just like a shortcut, but based on the product rule. Like there is a way we can derive it from the definition of the derivative, a bit like algebraically convoluted to get to, but there's an easy way to get to it. Given this manipulation that we've just done here, we've changed our quotient into a product, and then we could say use the product rule on this, and then where we might have to use the chain rule at the same time with that negative 1, we could basically do that same kind of little trick for any function, right? So I'm not going to go and finish off this problem yet. Right, so let's say we had y equals u on v. Again, just using u and v as shorthand instead of f of x and g of x. Okay, so this function we can write as, well, same way we separated it out there. Whatever the functions u and v are, we can write as u times 1 on v, and then we can write that as u times v to the negative 1. Alright. Now, what's the derivative if we're using the product rule? Well, if we're using the product rule, it's u dash times this one, right? So the derivative of this one times this one, okay? So u dash times v, or v to the negative 1, and then it's v dash u, so, but plus in the middle, sorry. V dash u, so, but instead of v dash, we've got v to the negative 1. So what's that going to be? Well, the derivative of this factor here, v to the negative 1, is really going to be not just v dash, but we're going to have to use the chain rule. So v to the negative 1, what's the derivative of this bit here? Well, it's going to be, bring the power down, subtract 1 from the power, and then times by the derivative of what's below the power here, v dash. And then this is all, that's a really scrappy 2, isn't it? So that's a dash prime derivative. And then, so the derivative of this term times by this one. Okay, so now we can just fiddle around with this to make it a little bit cleaner. This is u dash over v plus a negative is going to be minus. Then we've got v dash u over v squared. All right, and then just to get a common denominator, we can multiply this one by top and bottom by v. And then we're going to have, now that we've both got v squared, on the denominator, we're going to have u dash v minus v dash u. So this here is the quotient rule, u dash v minus v dash u all on v squared, which is just like a little trick using the product, combining the product rule and the chain rule. So you don't really need to do it because you can just write any quotient like in this form and then use the product rule and the chain rule, but the same kind of logic happens every time, so we can have another rule to deal with it, which might be more convenient in this format. If you watched the previous video, hopefully you're watching this in order, or maybe you just found this video, go back and watch the other one, help farm me views. Then you might remember that with the product rule, u dash v plus v dash u, the order of addition and multiplication there didn't matter, but I alluded to the fact that the order will matter in this rule. So that's where I was saying it's a good habit to get into for the product rule of doing u dash v plus v dash u instead of the terms the other way around, because in the quotient rule, there's minus in the middle where order does matter, so get in the habit of doing the u dash v minus v dash u. Okay, so maybe let's go back to this problem and try it using this rule. And if you wanted to, you could use the product rule here and see if you get the same thing, but just to showcase using the rule. So let's just rewrite it. We have y equals x on x plus 2. Okay, so what I'll do is let's write the numerator over here is x, and the denominator v is x plus 2. Not going to be too tricky. The derivatives off to the side here are 1 and 1, and then that one times that one first with arrow, and then that one times that one. So the derivative is going to be u dash v, so 1 times x plus 2 minus v dash u, 1 times x all over v squared. Okay, and then do whatever algebra is required. We can expand this out. 1 times x plus 2 is x plus 2, and then we're going to have some like terms. X minus x is going to be 0, and then we're going to have a positive 2. So that's the derivative of x on x plus 2, which hopefully if you did that using the product and the chain rule, that you can also get the same thing once you've maybe simplified it. Okay, so let's do a fresh problem, and I'm going to do the one from the product rule video. You might remember I said maybe in some context we might want to differentiate and then differentiate something again, and one of those terms was this. Okay, so here we're going to have to definitely take u to be the numerator. Now v we could take to be the whole denominator 2 root x, or it might be, we could take out 2 as just as a constant factor out the front somewhere. Might be easier to deal with. So then when we do the derivative, we're going to have that constant factor half times then whatever the derivative of 3x plus 1 to the 5 over root x is. Okay, so when I write my root x, I'm going to change that over here to x to the half, and now I need to do my little mini differentiation problems off to the side. So 3x plus 1 to the 5, brackets with an x in it to the power of 5, bring the power down, subtract 1 from the power, what's inside the brackets, and and then times by the derivative of 3x plus 1, which is 3. 5 times 3 we can simplify to 15. Alright, x to the half, bring the power down, subtract 1 from the power, multiply by that power, and then, again, pretty standard thing that happens. Alright, negative power becomes positive in the denominator. So, quotient rule, u dash v minus v dash u, all on v squared. So we're going to have this one times this one first, and then this one times this one. Okay, so 15 3x plus 1 to the 4 times root x minus, oh, haven't left enough space, lovely, v dash 1 on 2 root x. Let's just section that off. Woo, going on alright. V dash u, so 3x plus 1 to the 5, all on v squared. So v, remember, I took that factor of half out, so, but v wasn't the whole denominator 2 root x, just because it was a constant. So I was just using root x. Okay, so root x v squared. So, like I said with the product rule, depending on the context you're using for this for, yeah, that's an expression for the derivative. Is it nice and clean? Is my board work nice and clean? No. Is the expression nice and clean? Not really. I mean, there's some pretty straightforward simplifications we could do without too much work. So one would be, we can put this 2 back in the denominator, and root x squared is just going to be x. We could take 3x plus 1 to the 4 out of 15 times 3x plus 1 root x minus oh, my bad, that's the one with the 4 in it. Ugh. High quality content over here. 15 root x minus 1 on, if it's 1 on 2 root x, the other 3x plus 1 on 2 root x. What else can we do with that? We could find a common denominator with these two, or maybe to clear that 2 root x, we could times throughout the top and bottom of the whole thing by 2 root x. I feel like I should bother to do it because I didn't fill that with the product rule. So we can have 3x plus 1 to the 4. Then distributing this, we're going to have 15 times 2 is 30. And root x times root x is x. Then we're going to have, oh, actually that doesn't work out too bad. And then because we've got 2 root x over times 2 root x, we're going to have minus 3x plus 1. Make sure you write that expression in brackets because you're minusing this whole fraction, so you're going to end up minusing this whole numerator. Don't just write down minus and then write down 3x plus 1 because you're not going to end up minusing that one there. And then that's all over 2 times 2 is 4. X times root x, I guess we could leave it as root x, or maybe to get into 1 power, we could say x is, we could take it almost back to this, root x squared times root x, which I'm only bothering to write down because I'm going to do another step here, and we're going to have 3x plus 1 to the 4. 30x minus 3x is 27. X minus that one, not plus, all over 4 on x squared times x is x cubed under the square root. Ta-da! Could you rationalize that denominator? Maybe, but again, let me allude to another purpose we might want the derivative for. So just like I said, well, this was actually one piece in the product rule last video, where we might want to differentiate a function a second time or multiple times. Sometimes as well, we might want to solve an equation when a derivative equals 0. Well, if I wanted to solve when this derivative equals 0, well, if this equals, I'm going to write it in, why not? If I wanted to solve, again, you don't know the reason yet for the context, that will hopefully come later, but let's say we wanted to solve when in fact does this equation equals 0, well, we could times this denominator up to this side, and 0 times that is just 0, so 0 would equal the numerator. Or you could also think about it like this: if you've got a fraction, something divided by something, when does that equal 0? Well, only when you have 0, you know, like 0 over 5 is 0, 0 over 37.2 is 0, 0 over anything is 0. So it's only 0 when the numerator is 0. So that kind of bit there is irrelevant, and then we'd have like, oh, when is that 0? Well, when that factor's 0, or when that factor's 0, right? And do that kind of equation stuff. So hopefully that's useful to show. Maybe that's why it could be useful to bother doing the rest of the algebra to get to this point. But maybe if you're going to differentiate it multiple times or just sub in an x value, there is a case for it to leave it in a previous form. But now we've done chain rule as well as constant multiples and all 4 of our basic operations, plus, minus, times, divide. So now that we've got all that kind of stuff in our toolkit, it'll be beneficial now to go and look at other types of functions other than just x with some powers. But that's it for this video, so catch you later.